In this video, we're going to talk about a proof of a theorem regarding the Cauchy Riemann equations. And if you haven't seen those before, you might look at the previous video about how they're used and maybe how they come about. But what we're going to look at in this video is the following theorem and its proof. So here it is. So here's some setup. Let's let G be a domain in the complex plane. When I say the word domain there, I mean it in the topological sense, that G is an open, connected set. Let's let Z naught be x naught plus I y naught, and let's just let that be like a specific point in G. And let's say we've got a function whose domain is G and whose output is a complex number, and we're going to refer to the real and imaginary parts of this function as u being the real part and v being the imaginary part. So remember, u is a function of x and y, and v is a function of x and y. Some books just write u is a function of z and v is a function of z as well. That's okay too. The point though is that u spits out a real number and v spits out a real number. All right, so here is the theorem we're going to prove. So statement 1 in the theorem is if f is differentiable at z0, so remember complex differentiable, then the CR equations hold at z0. And again, if you're not familiar with what the CR equations are, you should look at the previous video in this playlist for an introduction to those. Again, this video is all about the proof. So if f is complex differentiable at z0, then the CR equations hold at z0. Now statement 2 says that we can almost go the other way. In other words, the Cauchy Riemann equations can almost tell us that the function is differentiable. What do I mean by almost? Well, it's not quite a perfect characterization. They're not quite equivalent. If I have one extra hypothesis here, that the partial derivatives of f with respect to x and with respect to y, if those are continuous in some disk centered at z0, just think near z0, and if the CR equations hold at z0, then that is enough to say that f is differentiable at z0. So again, what this theorem is trying to say that the CR equations are almost equivalent to f being differentiable, but not quite for all functions. They are equivalent whenever f has continuous partial derivatives near the point and at the point that you're interested in. So again, the focus of this video is to prove statements 1 and 2 of this theorem. So let's get into it. Oh, one more thing. Further, how do you actually calculate what the derivative is? How is it related to the partial derivatives of the function in the x and y direction? The complex derivative, right, f prime is what I'm using there for that notation. So the derivative of f at z0 is the partial derivative of the real part of f, that's u, with respect to x, plus I times the partial derivative of v with respect to x. And again, that's the imaginary part. So what are we saying? The derivative of f is just equal to the partial derivative of f with respect to x. Kind of interesting. All right, now let's get into the proof. So we'll start with statement 1. And remember, the hypothesis there was to suppose that f is differentiable at the complex number z0. And just reminding you, z0 has real part x0 and has imaginary part y0. That means that the limit as z approaches z0 of f of z minus f of z0 divided by z minus z0 is a complex number. So it exists and it's a complex number. It can't be like infinity or negative infinity. And remember, that limit as z approaches z0, you're in the complex plane, so there's tons of directions for which z could approach z0. So that means that this limit, though, exists and is that specific complex number no matter how z approaches z0. And just to give you a little picture, I've drawn you like a domain G, and I'm saying it shouldn't matter if z follows the blue path to z0, the yellow path to z0, or if z followed the red path to z0. You have to get the same thing no matter how you get to z0. All right, so in particular, what we're going to do is we're going to utilize that. So I'm assuming that this limit exists no matter how I approach z0. So I get this complex number no matter how I approach it. Well, if we're going to deal with partial derivatives, it makes sense to maybe let's approach in the x direction and let's approach in the y direction. So like think horizontally and vertically if you like. So let's start with, in blue, I'm going to talk about the limit as z goes to z0 along the line y equals y0. And I'm going to play around with what does this limit look like for this particular case. And just to help you visualize it, what I'm saying is if I plop z0 down somewhere, right? Remember its coordinates are x0, y0. I'm looking at what happens as z gets close to z0 just along that dotted blue line now. So what we can say then, if I know that z itself is approaching z0 along that dotted blue line, I can write down explicitly what z looks like. Z looks like x plus I y0. And what I just want to draw your attention to is that the imaginary component y0, it's fixed, right? That's y0. What x is allowed to change, right? X is allowed to approach x0. So that's going to allow me to rewrite the limit above. Oh, maybe one more thing before we get into that. Let's think about the difference, z minus z0. And let's think about what does that look like in terms of x, y's, x0s, and y0s. So that would be x plus iy, that's z, and then minus x0 plus iy0. And when you actually do that algebra, you see that the imaginary parts cancel. So you're just left with x minus x0. And so z approaching z0, that's equivalent to x approaching x0, right? There's no change in the y direction. And that should also be clear in my picture, right? You're going along a horizontal line. There's no change up or down. And so one more thing, let's talk about how can we write our function f of z, and how do we write it in terms of u's and v's, right? It's real and it's an imaginary part. And so what we just said is that, well, the imaginary part, y0, it's just y0 all the time, right? And so what this function looks like then is u of x comma y0, where x is like the variable. Really, I'm thinking of u as a function of just the variable x, plus I times v, same story. I'm thinking of v as a function really of just the variable x, right? I'm holding the y coordinate fixed. And now what our limit of this difference quotient looks like when I substitute this information in. So what have I done? Instead of z going to z0, we just got done saying that's the same thing as x going to x0. And instead of using the notation for f, let's turn it into its real and its imaginary parts, u and v. When I plug that information in there, here is the difference quotient that I get. And what you might notice is some things maybe simplify a little bit. Maybe they don't simplify, sorry about that. So what are we going to do? Let's split this into two pieces. Let's get the u pieces together, and let's get the v pieces together. In other words, the real parts and the imaginary parts separated. And if you allow me to zoom in a little bit, if I think about each of these two limits here, what's going on? That first limit, we're just allowing x to change, and we're holding y constant. And what's that called? That is the partial derivative of u with respect to x. That's the partial derivative of u in the x direction. So of course that's denoted by u with a little subscript x, and it's evaluated at this point x0, y0. And similarly, if you study the difference quotient involving u, same story, only the x coordinate is changing. X is approaching x0, but the y coordinate is constant. So again, that's a partial derivative with respect to x. And so that is the partial of v with respect to x. I'm using the subscript notation just because it's convenient. Okay, so we just simplified what does this difference quotient look like if I just approach, horizontally along the x direction, if you like, and I get that it's this partial of u with respect to x plus the partial of v with respect to x down there. That's its imaginary part. Now let's do the same thing up here. F prime, remember we assumed that this limit exists for all directions that I could approach z0. So now let's do this vertically. Let's say that our complex number z approaches z0 along the vertical line, x equals x0. And so I'm going to do all these computations in this kind of pinkish color. So just to give you a picture, what do I mean? I've plopped z0 down still, but now let's say, what if I go along this direction? What if I let z approach z0 along that dotted pink line? What I want you to notice now is that, well, really that's just the y coordinate that's changing as z approaches z0 along that dotted line. The x coordinate is always x0. And so if we wrote that down, what we're saying is that complex numbers that we care about then, as they approach z0, they look like x0, that's constant, plus I times y. So y, the imaginary part there, is the thing that varies. And so same idea. Let's think about what does z minus z0 look like in terms of x's and y's. And if you track through that, now the real parts should cancel. And so you just get I times y minus y0. And so as z approaches z0, that's the same thing as saying that y approaches y0. This is what we just uncovered there. And then one more thing, what does f look like in this case in terms, f of z look like, in terms of u's and v's? Well, z has constant real part x0 and then imaginary part y. And so this looks like u of x0 comma y plus I times v of x0 comma y. So that's what the function looks like, again, along that dotted vertical line. Now let's get into this difference quotient. So if you look at the pinkish difference quotient at the top, what is this simplified to along this line x equals x0? What we just did in white was try to justify that, look, as z goes to z0 along that vertical line, that's the same thing as y goes to y0. So notice we've kind of swapped out that limit variable. And then instead of f's, just like before, I'm going to write that same statement just in terms of real and imaginary parts, u's and v's. We're going to do the same thing where we take that fraction and we just split it up, right? So we kind of undo the common denominator, if you like. And then we're going to take, limit laws. We can take the limit of each piece, the real part and the imaginary part. And then if we study that a little bit, what do we get? So maybe if you allow me to zoom in a little bit, notice there's an I in the denominator of that first limit. And I know that that's dividing by I is the same thing as multiplying by negative I. And then what else do I want to study about that? We're looking as y goes to y0 of, if you study that difference quotient, you know the x coordinate is constant and it's just the y coordinate that's changing. And so what is that difference quotient whenever x is constant and y changes? That's the partial derivative of the function with respect to y. And so that difference quotient is u sub y of x0, y0. And then over on the in the second fraction to the right, notice the i's just cancel in that case, but then otherwise it's kind of the same analysis. The x coordinate is constant, it's just x0 in both cases, and then we're allowing y to vary. We're allowing y to go to y0, and so that of course is the partial derivative of v with respect to x. I'm sorry, with respect to y. That should be, whoops, that should be a y there. Okay, and so if I put all this good stuff together, what do we get? Well, we just said that these two things, or not, sorry, all of these things are equal, right? F prime has to satisfy both of these, and it has to give you the same thing. That's what we mean by this limit has to exist in all directions. And so the punchline is that now we can finally set these things that I've colored equal to each other. And remember, this should be a y right there, not an x. And so what do I get then? Finally, there we go. So the partial of u, when I equate, these complex numbers to each other, the complex number on the left has to be the same thing as the complex number on the right. And so that means that the real parts have to be the same. That's in red. So the partial of u with respect to x has to be the same thing as the partial of v with respect to y. And then in blue, we see that the partial of v with respect to x has to be the same thing as minus the partial of u with respect to y. So, and those are the Cauchy Riemann equations. So the Cauchy Riemann equations hold at this point x0, y0. So that was, in some aspects, the easier of these two statements to prove. And so remember, we just finished statement 1 up here in yellow, and now it is our task to try to prove statement 2. So what are our hypotheses for statement 2? We get to assume the CR equations hold at z0, and I'm going to choose to express the CR equations in the following notation. So that's just saying the partial of f with respect to x is minus I times the partial of f with respect to y. And again, you can kind of unpack that as a system of two equations with u's and v's, just like I had above, just remembering that this is a typo that doesn't want to stay. That's a y right there. So same thing, this is just an alternate way to express that system. But then the other hypothesis that we get in this for number 2 here, f has continuous partial derivatives with respect to x and y near z0 and at z0, so in some disk centered at z0. And again, it's our job to try to prove that f is differentiable at z0. So we want to show that f prime of z0 is fx at z0. And so if I know fx at z0 exists, right, that's what we've assumed here, then it's enough to show that f prime has that value. That, of course, shows that the limit, this difference quotient for f prime should exist as well. And so just another way to write that down, again, like I just said, I want to show that this limit as delta z approaches 0 of f of z naught plus delta z minus f of z naught divided by delta z. Remember, that's just the same difference quotient we've been dealing with. That actually equals the partial of f with respect to x at z0. And so think of delta z, by the way. Think of that as z minus z0 like we were doing above. And so if you put that in terms of x's and y's, that's x minus x0 plus I times y minus y0 when you kind of gather the real and imaginary parts. And then we're just going to call x minus x0 delta x, and we're going to call y minus y0 delta y. So in case there's any confusion between introducing a delta z instead of like a z minus z0 like I was playing with above, we're going to do kind of the delta notation for this direction. And so just one more thing. To say that delta z goes to 0, that's the same thing as saying z goes to z naught, so we're still, analyzing the same kind of thing. And then that's the same thing, if z goes to z naught, that's the same thing as saying both delta x goes to 0 and delta y goes to 0. So just so we're on the same page about how things are changing. All right, so in order to do this, and what do I mean by this? To try to show that this limit is equal to the partial of f with respect to x. So in order to do that, we're going to try to show that the difference is 0. And just think about if you took this and you subtracted it over, I want to show that that equals 0. And so that would be enough to do it. And so what we're going to do is we're going to manipulate that difference. So again, think about what if I took the partial of f with respect to x, that's in blue, and just think about if I subtracted that over to the other side up here. And so here's what we're going to play with. And we're going to rewrite the term in yellow, that difference quotient, in a funny way, and we're going to rewrite the term in blue, which is the partial with respect to x. We're going to rewrite that in an even more funny way. And so, by the way, too, that limit, it's going to be the same thing as if you put parentheses around the whole thing, just because, this is a specific complex number. You've plugged in z0 into that partial derivative, so that's a constant. And I know that the limit as delta z goes to 0 of a constant function is just going to be whatever the value of the constant function was. So it's okay to just put parentheses around this all together here. So let's get into how are we going to manipulate the yellow. And so if we're going to do one of the famous math tricks, which if you notice, we're going to add 0 in a very sneaky way. So I'm going to add and subtract f of z0 plus delta x. And then what I'm going to do is I'm going to, instead of delta z notation here, let's pull that apart in terms of delta x's and delta y's. So remember, that's the same thing. And then what I've done is I've split this into two pieces. So I'm going to kind of split this into this piece plus this piece down here. So I've just split up this common denominator into these two. Okay, now what we're going to do is we're going to take the blue and we're going to rewrite it in kind of a tricky way. So I've rewritten it there, and what I'm going to do is I'm going to multiply it by 1, of course in a sneaky way though. So 1 is the same thing as delta z divided by delta z. Remember, I don't have to worry because delta z is never allowed to actually be 0, right? So delta z is this funny thing that it represents something that gets infinitely small but never actually is 0. So I don't have to worry about this being undefined with delta z over delta z. And what am I going to do then? Well, delta z can be pulled apart a little bit. It says delta x plus I delta y. And then what we're going to do is we're going to split that fraction up. We're going to think of it as delta x over delta z times f with the derivative of f with respect to x plus I times delta y over delta z times f's derivative with respect to x. And then just one last thing here. What you've noticed that I've done is I've changed this derivative of f with respect to x, I've changed it to minus I times the derivative of f with respect to y. And what on earth, how can I do that? That's the CR equations. And this part of the proof right here, this is the only time we're really going to use the CR equations. It's to make this subtle change right here. And so just to rewrite that a little bit differently, I want you to notice that I times minus I is positive 1. And so all I get left then is just plus. Just this plus right here. Okay. So let's recap a little bit. What did we just do? We're going to consider this limit of the yellow minus the blue. And now what we're going to do is we're going to sub in, okay, what does that look like based on how I have manipulated the yellow expression and the blue expression. So here's the yellow expression that we just derived above. And then this should be minus then, again, just kind of tracking that red minus sign through there. And then let's put in, what did we get as our manipulated blue expression? And so this guy. All right, so it's more algebra to do. We're going to put this together and rearrange it in some funny ways. So let's put these two green pieces together here, and let's put these two pink pieces together here. And I'm going to do that in the next line. So I take this limit, and so here is me putting the pink pieces together. And one other thing that you see that I've done is, in white, I've introduced a delta y in the numerator and the denominator. So I've introduced this delta y here. Again, that's legit. That's just 1, and you'll see why I've done that in a moment. And similarly, I put the green pieces together and notice that I've also introduced a delta x and a delta x in both the numerator and the denominator. And again, that's okay because that's just 1. And so why am I going to do that? In the next line, do some more algebraic manipulation here. What I'm going to do is actually factor out this delta y and this delta z in the bottom. So I factor that out. And if you think about what you have left, you could factor a delta y over delta z off both of these expressions that are underlined in pink. And so if you factor that off of both of those, what you're left with then is this difference quotient, but now over delta y, and then that's divided by, then subtracting just the partial of y with respect to z0. And now I'm going to go over to the green underlined statement, and I'm going to do the same thing. I see that in yellow, I've got a delta x over delta z, and in the blue, I've got a delta x over delta z. And I can also, distribute this limit to that too. So I'm going to factor that out. So limit as delta z goes to 0. Factor out that delta x over delta z. If it's okay, I'm going to zoom in a little bit. And then here is what you have left when you factor that out. So I'm hoping it's going to become apparent in a moment. Why on earth is this good? What is the rhyme or reason for trying to do all this good stuff? And there's one more thing here that I want to notice just to get it out of the way. let's focus on both of these things here. Eventually I want to get to a spot where I can take the limit of each of these expressions, and maybe I'm worried about the limit of this delta y over delta z and the limit of delta x over delta z. But I don't have to worry about them because the modulus of these complex numbers never gets any bigger than 1. And how do I know that? So let me just demonstrate it with delta y over delta z's modulus. And so if you substitute the definition of that, remember delta z is delta x plus I delta y. And when you take the modulus of that thing there, you're going to get delta y squared over, so you can take the modulus of the top and the bottom, and then that's divided by delta x quantity squared plus delta y quantity squared. But then when I do that in this case, I'm going to divide everything by delta y squared. And now what I look at is it's 1 over something plus 1. And that thing in the bottom, if it gets small, fine. If that gets small, then what do I get? I would just be left with something like 1 over 1. And if that got huge, well then this fraction never will get any bigger than, or this fraction would probably go to 0. So what's my point? This is definitely less than or equal to the square root of 1. Maybe another way to think about that fraction right here, this is 1 over some positive thing plus 1. So 1 over a little bit more than 1 should be less than 1. And so that is how I want to think about this. And so why is that important, of course? Well, eventually I want to take the limit of each of these expressions, but maybe I'm worried that delta y over delta x, or delta z, maybe I'm worried that that's like indeterminate, right? What if it looks like 0 over 0? And then it makes no sense to even think about what these limits do anymore. Or maybe the analysis I need to do is much more difficult. But the fact that these are now bounded, right? Their moduli are bounded, I know that it's not going to be an indeterminate thing, so that it suffices to just think about the limit of the expressions that are in the parentheses from now on. So we don't encounter an indeterminate form, so we can just look at what's going on in the parentheses. So let's get into that then. So just to kind of clean it up, I'm going to recopy, or I guess really just one copy from above, that exact same statement though. And now what we're going to do is we're going to look at each of these two pieces. And so let's focus on this one. So I'm going to do this work in blue. And let's see, what have I got? I am allowed to now think about these limits separately, right? You've got this product, and we just argued that, well, this isn't going to affect whether this one converges or not, if that makes any sense. And so if I think about this limit over here, well, as delta z goes to 0, that's the same thing as delta x goes to 0 in this case here. And what I want to notice, how do I know that? It's because there's no change in y, right? Y is constant. Y is not changing. So delta z z changing just says x changes, right? If you look inside of these parentheses about what's going on, right, only x is changing. So delta z going to 0 is the same thing in this case as delta x going to 0. And now what I want to realize is that, well, if delta x goes to 0 and x is the only thing changing while y is constant, that's just the partial derivative of f with respect to x. So this piece here, when you take that limit, is that partial with respect to x. And now what I want to notice is, well, inside the parentheses, those are the same thing that you're subtracting. So of course that's 0. And so what do we get? We get that whole piece that's underlined in blue, right, this whole limit up here is just 0. And that's good. Remember, we're on our way to trying to show that this whole right-hand side of the equation is equal to 0. That's our goal. So that piece is 0. And now it remains to show that this limit is 0. This one's a little bit tougher though, because if I zoom in on this, and by the way, showing that this limit up here is 0, that's the same thing as showing that, well, the limit of this is equal to this number. And that's the notation that I have chosen to run with down here. So showing that the limit of this difference quotient being fy over z naught is the same thing as the partial derivative of f with respect to y, it's not an obvious thing to do. And let me just say a little bit more about why is it not obvious. It's because the definition of the partial of f with respect to y, I know that holds x constant while y changes. But notice here, well, delta x is in there, right? That says x is changing too. So I can't just swap out this for a delta y, right? I've got to consider what's going on with delta x as well. So again, that's why we have to do some work in order to try to justify this statement here. But it is going to be true. Otherwise, we'd stop the video earlier. So in fact, establishing this limit, this is where we're going to actually have to utilize the fact that u and v have those continuous partial derivatives at z0 and near z0. Remember, that was like the extra condition in order for the Cauchy Riemann equations to imply that a function is differentiable. And so we're going to go ahead and we're going to prove this statement now. So this is the last thing we're going to look at. So let's rewrite f of z naught plus delta x plus I delta y, again in terms of u's and v's. And if you do that, it should look like u of x naught plus delta x, comma y naught plus delta y, plus I times v of x naught plus delta x, comma y naught plus delta y. And then let's also, and by the way, what is that? Why am I doing this? Let me go ahead and just grab a new color here. Why am I doing this? I'm going to translate this and try to just get z's kind of out of the picture and introduce u's and v's. And I'm saying that that is going to be substituted. The u's and v information there is going to be substituted in for that f information. Similarly, here is this expression, f of z naught plus delta x. Let's change that to u's and v's and get z naught out of the picture. Let's change it to x naughts and y naughts. And so that is me doing that right here. And you can track through why f looks like that in terms of u and v. And so now let's just go ahead and put that in. So that difference quotient with f and z naught in there, that's the same thing as, so here's me substituting the u information and getting it together. And by the way too, what have I done? What I'm doing is this minus this would be this minus this right here. So I hope that you see that. So I'm going to subtract these two expressions, and that's this. And the other thing I'm doing is I'm dividing by delta y. So divided by delta y. And then just before I move on, when I subtract, I also care about what I get when I subtract these two expressions right here and divide by delta y. And that's going to be the next step. But just so you see that we've done all this work to make this substitution, and now we are actually doing a little bit of an extra step and subtracting and gathering the real parts and the imaginary parts. Now we're going to do the same kind of thing where we want to look at these two things and try to analyze what's going on. So let me zoom in a little bit on, let's look at the real part here. So that, if you notice, here and here, right, the x-coordinate's the same, it's constant. But what have I done? I'm just saying that what if we're a little bit away from delta y? And then divided by, what is that teeny tiny change in delta y? So remember, like, what does this fraction represent? That's the average change in u. Or in other words, you know, if you think from Calc 1, this is similar in Calc 1 when you were looking at, oh, that's the slope of the secant line from A to B, right? Again, and I'm not trying to visualize that here, just trying to make a connection for something you're probably familiar with. So this difference quotient is the average change in u from these 2 points, x naught plus delta x y0 to x naught plus delta x y naught plus delta y. In the y direction though, right? So like y is the thing that's changing, so that's the direction that we're kind of moving around in. And another way to say, what do I mean by in the y direction? Remember, for partial derivatives, we mean with respect to this vector e2, which is 0, 1. Again, just think about it going along the y-axis. And if we look at this difference quotient that involves v over here, it's the same story. That's going to be the average change in v in the y direction between those 2 points, x naught plus delta x y0, x naught plus delta x y naught plus y delta y, sorry. And so what do we know? Is there something, you know, what's our goal here? Maybe I should remind you of that. We want to bring in some information about partial derivatives, and we're changing in the y direction. So we're going to try to bring in some information about, well, how are these related to like the partial of u with respect to y? And how is this second fraction over here related to the partial of v with respect to y? And what we're going to dig deep and think about is, oh yeah, there was the mean value theorem. And the mean value theorem told me what? So u and v both satisfy the mean value theorem since I can take their derivatives. And what's the mean value theorem say in a nutshell, like the gist of it? If you've got 2 points A and B, then there's some point C that's between them such that the average change in your function from A to B is the instantaneous change at C. All right, so again, the mean value theorem was a relationship between, kind of in Calc 1, it was the relationship between the slope of the secant line is eventually going to be the slope, or is at some point going to be the slope of the tangent line. All right, so then let's write that out. What's that look like? So if I apply that, this average change in u with respect to y, what the mean value theorem tells me then is that that should be the partial of u, right? The partial of u is the instantaneous rate of change in the y direction at this particular, at some point. What do I mean at some point? I don't know where exactly it is, but it's on some little line segment that connects x naught plus delta x some little line segment that connects this point to this point, again, in the y direction, right? Notice that it's just somewhere between, some point between there. I think I've got a little picture for you over on the side. Just by the way here, just to try to relate it to my kind of off the cuff, what's the mean value theorem? What's the gist of it? So I'm saying y naught plus a delta y is c, and then y naught is a, and y naught plus delta y is b. So if you want to try to relate this back to what am I trying to tell you about with the mean value theorem, you can think about that. And then you can make a similar statement for this is the average rate of change in v, and that should be equal to the instantaneous rate of change in v in the y direction, right? Somewhere between this point and this point. And so that's for some b between 0 and 1, you get that y coordinate there. All right, so if I put all this good stuff together, what I'm going to do is I'm just rewriting the statement about here's the difference quotient and the f notation that we're interested in dealing with, right? And so far what we've said is that, all right, that's the difference of these two average rates of change in a y direction. But what we just uncovered with the mean value theorem is that, well, that average rate of change is an instantaneous rate of change somewhere in the y direction for u. And similarly, this average rate of change for v, somewhere it's an instantaneous rate of change in the y direction for v. And so now what we're going to do is we're going to take the limit as delta z goes to 0 of all sides of this. So I'm going to take the limit as delta z goes to 0 of this. And remember, that's the thing we're interested in computing. What I hope it is it's the partial derivative I'm interested in. And then that's going to be the same thing as taking the limit as delta z goes to 0 of both of these, right? Since these things are all equal. And so let's go ahead and do that. And so what do I have then? The limit of this difference quotient I'm interested in should be equal to, well, the limit of this partial derivative as delta z goes to 0 plus I times the limit of this partial derivative as delta z goes to 0. Again, I'm just taking the limit of the right side of the equation. But now what is that on the right side? Here's where we're going to utilize the fact that uy and vy are actually continuous. So this is where we need that extra hypothesis here. Because when I take that limit, as delta z approaches 0, what's going on? That just makes sure that whatever these points are inside, it ought to just be what the output is at x naught, y naught, right? That's what continuity says, right? The limit needs to just be the output at the point that you care about. And so that's this right here. And similarly, since v has a continuous partial derivative in the y direction, again, this limit ought to just be the output at vy at this particular point I care about, right? Like since we're getting close to that point, continuity says the limit has to be the output of your function at that point. So that's just the partial of v with respect to y. And so what is that then? Partial of v with respect to y at my point plus I times the partial of v with respect to y at my point. That's just the partial of my function f, my complex function f with respect to y at my point. And so what do we get then? We just finally show that this is equal to this. And if I scroll back up to 20 years ago, remember, we said that that is what we want to show, right? That is what we want to prove. Because what we just justified then is these two things are the same. So you get 0 when you subtract them. And so if you scroll back down, sorry if I'm making you motion sick, when I come back up to all the work we've done, just to recap, we just figured out in purple that this much is 0. So this whole limit is 0. And then remember we did all this work earlier in blue that said that limit is 0. So this limit equals 0. And the last thing you could do is you could just add this to the other side since the other side is 0. And so I get that here is my difference quotient, right? As delta z approaches 0, I get that that is the partial of f with respect to x. And of course, this difference quotient, when you take that limit, that is f prime at z naught. And so finally, what is the derivative of f? What's it look like with respect to x? Remember, that's the partial of u with respect to x plus I times the partial of v with respect to x. And so we just show that yes, the derivative exists, and it's equal to this here. And all we needed in order to show that the derivative existed was the CR equations, and again, this fact up here that we can use continuity to evaluate these two limits.